If you want to get started with the setup and have some ready, you can just go to the repository there. You can maybe make it bigger. Well, anyway, it's GitHub/ppmon/retest language project tutorial. The instructions are in this welcome notebook, but in short, what you're going to do is on the main code page, you're going to go and create a code space by hitting the ... New with options, and you want to, it should be in US East. That's where rebuilds are available, and you ideally want at least 4 core code space. I know when Anjali tried earlier, there was no 8 and 16 core for her, so but you can use whatever you want. Just ideally 4 would be great. Everything does run on full cores. I'll go over this later also.
Good? Not bad. Yeah, edible. A little bit. You still got plenty of room? Okay.
Also, if you did already go through the spinning up of the code space, in order to kind of see when it is ready, you can take a look. Let me go ahead and line this up. But you'll basically, as in the welcome notebook, it says, you'll see in parentheses Leech-test live-wing probability tutorial in your terminal prompt. That's an easy way to make sure that all of the pre-built steps have been done, and that's essentially activating your virtual environment. So, okay, right there. Okay, get started.
Hello everyone, welcome to your second event here at PyData. We have DPMN and Anjali doing a session on building machine learning pipelines and scale. Thank you.
All right, thank you all for coming. Just by a quick way of introduction, my name is Ibis. I am a software engineer, primarily working on open source Python stuff. Very much fits in with the whole Python PyData thing. So we are going to today talk about a number of like open source tools, including Ibis and Ibis ML. I was part of the core Ibis team up until quite recently, as well as kind of the primary lead on Ibis ML. In addition to that, kind of work on contributing to other stuff in the Python data ecosystem, like data pipelines with Kedro. Also just excited about these tools in general. We can talk about DLT, another open source Python tool, as part of the presentation as well. I'll let Anjali introduce herself.
So I'm a postdoc at Stanford Medicine, and I work on processing MRIs for various things, and all of those data someone who hasn't worked on Ibis ML can still use it.
Yeah. So just from an overall kind of structure perspective, we're going to start out by talking quickly about like data ingestion. Then we'll spend a while. I'll cover primarily the feature engineering aspects using Ibis. Anjali will talk about how you can then use Ibis ML for some of the ML pre-processing, and then we'll kind of wrap up by demoing how this can all, as we get in the title, how we can actually scale these ML pipelines. So that was a quick introduction of ourselves. That's the explanation for why we are, I guess, technically qualified. But how can we actually talk about some of this lead chess, or like how to build like a chess like win probability model? So we are also qualified from a chess perspective, apparently. So this is the last picture we have together. So yeah, we've been playing chess for most of our lives, and excited to kind of combine this with some of our interests. All right, so we will get started. Okay, let me go here. So just out of curiosity, have people been able to spin up the code space? Okay, if you have any issues, let us know. Real quickly, going to start by talking about data ingestion. And also for people who did come a little bit later, for the code space, what you will just go to is this repository, ppmon/leadchess live win probability tutorial. There's a link in the event thing for attendees as well on the schedule, and you can follow those instructions here. Make sure that you spin up something with at least 4 cores on assist and wait for it to. Right. Okay. So the data that we're going to be working with is from LeadChess. If you're not familiar with LeadChess, LeadChess is a like chess server. And you've heard of chess.com if you haven't heard of LeadChess. Cool thing about LeadChess is actually it's all open source, nonprofit, and it's the second largest chess server in the world. The other cool thing about LeadChess is that they have that's not live, right? If you go to database.leadchess.org, they freely share all of their kind of like historical game data. So in order to do this, we have actually gone ahead and pre-ingested data for, I believe, September of 2024. It takes quite a while to ingest it. As you can see, like this is almost 30 gigabytes of data. We're also going to be working on like a subsample of this together, and then we'll kind of show how it can scale later. But how do we actually do the ingestion? Just want to quickly cover that. So we use DLT for data ingestion. For this, we are working off of in this case from the file extract. And that is stored in our data directory. You can see that when we are running this down here for which file we're processing. DLT basically works that you're able to kind of it's a pure Python open source tool. In short, you're going to be able to emit records coming from some source, or if you're defining a custom source, then maybe use one of the built-in sources. Here we're doing a custom resource, which is getting our games and moves. You can do some cool things. This was part of my learning experience with DLT, that you can actually write out to a couple of different tables. So we're going to produce games and moves tables. And you can choose where, when you run your EL pipeline, your extract and load pipeline, where is that going to go? So in this case, we are actually writing this to a file system destination. So this is to a data folder on my local machine. One of the things which, as we're going to scale, scale doesn't mean that you're going to just be running using some distributed engine and targeting data on your local machine. So you can also change this to a lot of the built-in destinations. So for example, we'll see later on how we are going to run against some data that's been ingested into S3 already. So actually we have the full data set on S3. Yeah, that's probably about it going to cover for DLT right now. If you do have other questions, more than happy to kind of talk about the ingestion process and things after. I know that Violetta from DLT Hub is also here, so I'm sure she'd be happy to answer any questions and stuff around that. Cool. Let's move on to feature engineering. So just out of curiosity, has anybody here heard of Ibis, used Ibis before? Okay, not too many people have used it, but it seems like some people have heard of it. Just out of curiosity, did anybody attend the Big Frames tutorial just earlier? All right, so whoever did attend the Big Frames tutorial, you technically also used Ibis. So they use Ibis under the hood. I think it's a vendored Ibis. Tim is actually, I think you're a maintainer of Ibis. A steering committee member. Yeah, I am not, so he probably knows more about Ibis than I do. But yeah, so you should be able to run this for cell. If people are running into problems, just let us know. One thing you'll notice is that you're up in this corner. It should say the .vn. This is a pre-configured environment. We should have the dependencies installed. All right, so so we're not going to go too much into the basics of Ibis. What you can kind of know about Ibis is that Ibis is a data frame library that allows you to target whatever backend you want. So there's I think about 20 backends that Ibis supports. So there's not really a question of oh, how does Ibis perform against pollers or against BigQuery or ClickHouse or something like that. Ibis is more like an abstraction layer that allows you to use any of these under the hood with the same kind of familiar data frame syntax. Part of this is that it allows you to write kind of backend agnostic code. By default, your backend is going to be .db. .db just turns out to be a very powerful, efficient local backend. One of the main reasons people might not like .db is because it's SQL, not Python, but Ibis provides a Python data frame interface on top, so problem solved. From that first import, you'll also see that we are using this in interactive mode. If you're doing a production workflow, you probably don't want to do in interactive mode because that's going to, at each step, it's going to automatically evaluate your data, but or at least the preview that it's going to show. However, for the purpose of kind of exploration, interactive mode can be a very helpful thing. So we can see here that we have some of this game data. So we've got our game ID, and we have information about when, link to the a link to the game on the site column. That's where the game ID is actually extracted from, as well as a number of other fields. So this is what our game data looks like. In addition to that, we briefly saw during ingestion that we have move information. So as part of our data ingestion, we have essentially our like top level game metadata, and then for each move, we will also have some of the important data that we want to look at from a modeling perspective. So also before kind of like go too deep into this, you probably said, what are we actually trying to do here? We are looking to build a live string probability model. So I will let Anjali like talk more in depth about the model later, but at a high level, what we're trying to do is we're trying to essentially predict what's the likelihood like a player is going to win, lose, draw at any given point in the game. So I mean, even if you're not familiar with chess, like sometimes you like let's say you're watching soccer on the TV. I think nowadays like sometimes they put like, oh, what's the like live win probability sort of thing. They've done live win probability for the election, but I don't think anyone wants to talk about that right now. Yeah, we're going to start out by just doing some basic feature engineering. Here we can just do an exploration of our data. So we can see that for our event column, we can like this. They start with a variety of different substrings. We can see that the event column is actually encoding some different information. So there's an optional rated prefix, and then what is the like time control? Time control is essentially we'll try to not get too chessy here, but like essentially like how fast the game is. So you can think that Blitz is like pretty fast, like 3-5 minutes per side. Bullet is even faster. Ultra Bullet is like generally fast, like you're playing in seconds. Rapid games are maybe I forget the exact, I think it's like after 8, like longer than 8 minutes total. Classical is maybe like more than 25 minutes total per side. One thing to note is that each player has their own clock, or has their own timer for chess. So we can go ahead and create some features. So for example, we can extract whether whether the game is like a rated game or not. This might be interesting to look at because people might care more about rated games, like more seriously, something like that. We can see the vast majority of our games are rated. And one thing that we're going to do is we're going to keep track of each of the features as we're building them. So here we're going to go ahead and add them to a list that we created. I will say just as a caveat, if you're following along and you just happen to kind of like go off from just doing like, oh, press shift enter yourself, just make sure that when you add something, like you don't add something to the list multiple times, or if you do, then just make sure to kind of remove them because we're going to use this list of features to like create our final table later, and if you have duplicates, then you'll end up conflicting names. So that's just something to keep in mind if you do run into that later. Okay, so what else can we potentially extract from this? So we can take a look at like the time control, like we said, right? So in order to extract that time control, again, we can use pretty familiar syntax here. So in this case, we're going to look at the substring after that initial, after stripping that optional rated prefix. If you have questions about the specifics of Ibis syntax, this is all kind of like there's like much more detailed documentation on ibis-project.org. I think we'll throw some links into that later as we kind of get into some exercises. But yeah, we can figure that out, and we can see like here we have lids, classical, bullet, correspondence, or like essentially untimed games, and so on. And let's not forget to add this to our list of features. that actually brings us to our first exercise. Yes.
I'm sorry, but can you go over the purpose, like the ultimate purpose one more time? I kind of went over what we're trying to accomplish.
Yeah. So what we're trying to do is we're trying to build a not great, but just basically like a live win probability model. So that's basically going to say that like at any given move during the game, what is the likelihood of the outcome? Like I said, Andrew will kind of go over this more later, but like we'll essentially say like, oh, if white's gonna win, or if we think white's gonna win, it'll be like a high, like close to 1 score, and if black's gonna win, it'll be close to 0, and draw is equal likelihood, it'll be like half.
Okay. Got it.
Yeah. And then like why do we not just don't want to kind of jump the gun too much, but like we do also have like game evaluation information. So like if you ever do watch us online, you'll see like an eval bar, which is showing like what does the computer think of this prediction. But we believe that there's other factors that go into that other than just like how does it work.
So these features that we're building are trying to predict that ultimate outcome of A wins, B wins, or a draw.
Correct. And we are, so right now we're creating essentially game level features. So these are going to be not like, these are going to be the same across each of the moves in a game. We'll get to some more interesting features right now, like around, the individual player strengths and so on. This is also going to just be like a quick subset of things to build a very simple model. There is actually like, if you look at the, it's not like fully cleaned up or anything, but if you look at the repo without like dash tutorial on that, so github.com/dpmon/live win probability, like that's kind of a more full, like that's where it was kind of working on like a more full set to like do a realistic or like a good model. I think that that's something that we want to kind of continue work on in the future, but for now, we want to focus on just like a very simple set for this tutorial. So like we were saying, we are going to start off with an exercise. So what we want to figure out is whether a game was part of a tournament or not. So as you can see from looking at like some of the values of the event column, you can figure out from here that we have like rated blitz tournament or rated ultra bullet tournament. So whether or not it contains that tournament field can be essentially our is tournament feature. We can just take a couple minutes to try and fill out this line of code. If you do feel like you have it, if you execute the line below that, it will pull up the solution and you can take a look if that looks right or not. Like, so if you think that you have the solution, just feel free to raise your hand. Maybe you can get just a rough idea of how people are coming along. And as a hint also, I should probably mention, the contains is a link there to the documentation for the contains function. which is probably the easiest way to figure out whether it contains tournament or not. Anybody have it? Okay. Looks like some people have it. I'm going to go ahead and continue then. So yeah, what we could essentially do here is we could do something like contains tournament, capital T. Games.event contains tournament. And if we want to quickly look at a distribution of that, we could look at value counts for this. So most games are not tournament games. If you have that, then that's great. If you just want to take the solution, or you're not sure if it's correct, if you just run the solution cell below, most of these are structured so that is going to, the first time you run it, it's going to show the solution cell. You have to actually run it again for that to occur, for natural logic to get executed. And once we do this, don't forget to add this to our list of game level features. You will notice that whenever we add a feature, we're actually giving it a name for the column. So like this tournament. On the other hand, you'll see this auto-generated, sorry, not that, but here, the auto-generated name is more based on the functions that are being used. Okay, let's get to some more interesting features. So one of the features that we really expect should help is looking at the relative strengths of players. So in chess, that is determined by ELO, or an ELO rating. And we can just, so we have these columns in our raw data. So if we just look at that real quickly again, you'll see that we have white ELO and black ELO features. However, these are strings. We can use the cast function to turn these into integers. Quite simple, and add it to a list of features. We'll just use the 3 raw features. Another thing that could be interesting to look at is whether a player has a title or not. A title is if you think of the top players in the world, like Magnus Carlsen, Hikaru Nakamura, people like that, they'll all be grandmasters. There's also titles for that are gender specific. Their women's title, which only women are allowed to get. They can also be, they can also have just the general open titles as well. And we have a variety of titles possible. So this is in the white title field. We can just, and white title and black title field. We can take a quick look at this. There's actually a lot of different titles. We will also notice that most players do not have a title, or at least don't have a title associated with their account. So for example, WGN is Women's Grandmaster, WCN is Women's Candidate Master, and so on. Let's just go ahead and add these as features. Okay. Next, one of the things that we're particularly interested in is looking at how time affects it. So in addition to having that kind of string description, whether it's a classical game or rapid game or something like that, we can also extract stuff from the time control field. So if we look at games on time control, you'll see that it has this format. So all of the games in the Lichess database are represented essentially as a base time, which is how much time each player starts with at the beginning of the game, and then an increment, which is how many seconds do you gain after each move. So for example, this first one, 180 plus 0, means that white and black both start with 180 seconds or 3 minutes on the clock. and gain 0 seconds per move, so there is no movement. Similarly, here we see 180 plus 2, which would be 3 minutes per side with 2 seconds gain per move. So we can extract each of those components out. So here we are going to, again, use some string manipulation functions. And we can take these and add them as some additional features for our model. Okay. Last but not least, from the game level perspective, we're going to also just do our target engineering. So this will be like what we're actually trying to predict, kind of going back to the earlier question. And what we want to do here, we're going to just use a very simple representation for the target, in that a white win is going to count as 1, a black win is going to count as 0, and a draw is going to count as 0.5. So we can see that it's about the same number of white wins and black wins. White wins a little bit more often. White has a slight advantage. It's pretty expected. Fewer draws. We're basically just mapping 1, 0, half, half, and 0, 1, which is the chess notation for the result. Okay. Cool. Now, we did kind of briefly say earlier that we're creating this like list of features. One of the interesting things is that, like, even though we're running in interactive mode, we're seeing all of these kind of outputs for what does this feature look like. These are actually just expressions in Ibis that can be that we can kind of also use downstream. We were actually using some of these expressions in computing some of the other expressions. So what we can do is we can simply select our full set of expressions from our table. So you can see here that we just basically did a select statement. We selected our game ID key, as well as we splatted out our list of features. This is why we were just adding them to a list. And you can see them now all added with their nice little names. So we see is-rated, time control type, elo features, and title features, and all of the other things that we kind of worked on. Finally going down to our target. Okay. If you did run into any issues there, feel free to let us know. We can maybe help you out, but going to kind of move on in the meantime. All right. So the next thing that we want to look at is our move level data. So let's quickly explore that. You'll see here that we are going to read from this parquet file using the wildcard. Again, default backend here is DuckDB. So this is just using DuckDB's parquet reading capabilities under the hood. DuckDB is actually quite good about just, since we have a fair, not a huge amount, but like a decent amount of data, DuckDB actually is able to just access that without actually loading it into the database. So what does this look like? We have actually pre-filtered this data. So if we look at an example in the database here, this is what the data looks like. What we looked at is this upper half of the data, which is kind of your game metadata. First, that's what we stored in our games table. Now we're going to look at the per move aspect. So for each move, you will see that this, like the data that we have a per move evaluation. That's the computer, in this case using a computer program called Stockfish, in order to figure out what the semi-objective evaluation for the position is, as well as a view of the amount of time left for each player. Just as a note, we did pre-filter this data in order to remove. So for the data that we have here in our data folder, we removed all the games that don't have evaluations. So about 10% of the games have evaluations. In order to make it something smaller that we can push to the GitHub repo, we have removed that already. So again, we can go ahead and create eval-based features list. And we're going to use a library called chess. Yeah, go ahead.
Sorry to keep interrupting. Can you go back to that last where you showed those things? Yeah. So I don't think I really get what those two, what you just explained there. You're saying that like there's a database of all these positions that account for all the pieces, both on the black and white, and an evaluation of those who has a comparative advantage at that with that chessboard.
Yeah.
Is that what that is? Like, so there must be gazillions of permutations, but are you right?
So yeah, let me try to explain this better. So essentially, what we have is a record of all the games that are played on the Lee chess test server. So
Okay.
here we have a game between white is German 11 and black is Lusaji, I don't know. And so these are just like their online usernames, and we can see like, oh, okay, first, like this is kind of just how the game went. So we see that here on like the third move for black, or the sixth flag, which is like a half move, that we're seeing that black played e6. This is like a chess notation.
Yeah.
Initially, I kind of like skipping over this, but essentially means he moved his pawn to the e6 square.
Right.
And at that point, we see that the evaluation from the computer is negative 0.04. This means that black has, it's 0.0 would be equal, it's like pretty much equal, maybe the tiniest, like nobody would care.
So it goes from 0 to 1.
It goes from, so the evaluation will go from like negative,
Negative
like
1.
anything, no, like
Negative.
it could be like negative like 20 or whatever, to like positive, like whatever. There's not really a clear cap on this. So the scores here, and I think we'll talk about this briefly, is in units of like pawns. So pawns are like the
Okay.
weakest piece.
Got it.
If you look down the road, actually maybe I can, let's just jump through this game a little bit. So at this point, we can see that black has a negative, or the evaluation is negative 2.7. So that is an advantage approximately equal to a bishop or knight in chess, and for black.
So let me see if I can summarize this. So this database has many games that were played by people that were recorded, and in each point in the game, there's an evaluation of who has a slight advantage over the other, based on a certain number of pawns of advantage or disadvantage. Okay, I got it. Thank you.
No worries. Yeah. Sorry. Like trying to, like have tried to not go too deep into the chess thing, but obviously it's.
I just don't want to get lost in this.
Have a like wrong bias also in terms of like, oh, all of this just sounds like whatever we talk about on a daily basis. So yeah. Yes. One more
Just a
question.
quick follow-up then.
Yeah.
Are those scores the cumulative, like tally of like what is the current status of the board, or is it per move? Like this move cost that player minus something
So this is going to be your like current status of the board.
of the whole board? Okay.
Yeah. So after this, I thought it's a negative 2.7. I guess it's a negative. Oh, it's negative 2.7 here. What it basically means is that black has that advantage at this given point in time. There is a separate sort of measure which you can look at of how good each move is. So like, for example, the fact that this went from negative 4.1 to negative 2.7 means that black did not make a great move, because if black made that ideal move, it would have stayed at negative 4.1 if he played perfectly. And so like, this is something that like you can kind of look at accuracy as for the computer, and this is called like average center pawn loss over your game, but that sounded way too deep into the like chess suite, so she made me think some of those out, which is probably probably a good decision. You will see, for example, that the engine is like putting again, maybe too much information, but this is like a double question mark. So that is essentially viewed as like a blunder in chess because the evaluation went from almost even to a big advantage for black after white made up 4 moves.
Thanks a lot for the questions, by the way.
Yeah. Okay. So this is all also like in a particular notation. We have something called, like, there's a library, open source library called Chess, which allows us to parse some of this. So we can look at, for example, for parsing, evaluation field contains a lot of information, so we are just going to use this and kind of trust that it works in order to extract that out. So if I go here, we've just imported that from the chess library. Ibis provides that like data frame syntax to do most of your computations. However, for certain things, there's also this escape hash that you can just execute SQL with Ibis, which is what we're going to do here because we're looking to do some very specific sort of regex functionality. Regex is one of those areas where it's difficult to create a common abstraction layer across all these databases because they all treat them somewhat differently. Datta D actually has like fairly nice support for it, and we can extract out fields like our mate and our like regular validation. We'll talk a little bit more about these later. And we can see here there's only regular val fields, but if we look at some particular game, we can see, for example, what this mate score looks like. Mate score, so checkmate is like when a player wins. If we look at like a positive mate score indicated by like the hash symbol, that basically means that in this case, white can technically force a mate within 10 moves, within 9 moves, within 8 moves, and so on. The easy way to think about this is like a mate evaluation is stronger than any like numeric evaluation because like it doesn't matter how much material are ahead. Once you get mated, the game is over. So if you can force a mate, then you're winning. Yeah. So numbers closer to 0 are indicating a more winning position from mate. We can take a look at what's the kind of maximum mate within our database. Apparently, there are like mates in 121 moves. Nobody ever actually thinks about like mates in 121 moves. Most games don't last 121 moves. But kind of as we said, like it's not really comparable across mate and these regular evaluations. So at least for the mates, we'll just kind of normalize the feature so that we're gonna look at as like a higher number being closer to mate. So a higher number is better if it's white, a lower number is better if it's black. So for example, there's some examples here. So 999 would be made in 1 for white, a negative 999 will be made in 1 move, black of course that. So black is about to win. Okay. And then we will go ahead and add these to our list of, in this case, eval-based features, and we can take a quick look at what this looks like. We just parsed a couple of fields out of there, so not too much. If we look at it for a particular game where we actually have mate score as well, so we can see here at the end, our feature for mate eval is going to be this mate in 10 because it's 990 for white. So and that'll be decreasing at the end of this game. I'm not 100% sure. Maybe it's quite possible that black just gave up or something. All right. Next, we're going to also parse out that other stream, so the clock information. So we can do this in a very similar way. You'll see that there's a link here for the clock regex from the chess library, and so you can use that to extract the information. So we'll give like a couple minutes to do that. Also, if anybody has questions in the meantime, more than happy to do it. Yep.
What are the cool advantages of using Ibis here?
Yeah. So one of the nice things is that we're using Datta D under the hood as Ibis's default backend. Even with this volume of data, if you try to process it using pandas, or especially on something without sufficient resources, it's going to be either slow or kill your kernel. I think in a lot of cases it will kill your kernel. You could, of course, also use something like polars, or you can use the polars backend for Ibis for this. That would probably also work. Another nice thing is essentially lazy evaluation. So if you were to use pandas for this, you'd be running everything and fully evaluating data set. Here we're looking at the preview, which is each time just pulling a sufficient amount of data to generate the preview. We will actually see so these operations have been near instantaneous. We'll see operations will just take a little bit longer, just a bit further down. And then the other part, which I'm very excited to show later, is the fact that we're not tied to a particular backend. So we are using DuckDB, which is great for your local experience, but just using like a local DuckDB may not be the best way. We could process 30 gigabytes of data if we have a good enough machine, but we could instead process more data and do bigger queries if we're using some distributed computing framework. So we'll show that using Trino on Starburst Galaxy in the cloud, and we can do that without essentially changing our code. And so that's one of the big benefits of using Ibis that I want to show. Yep.
So DuckDB has SQL syntax sugar that others don't.
Mm-hmm.
If you write that in there, that's not going to be portable then, correct?
Correct. So that's why this .SQL is basically an escape hatch. What we mean by that is that Ibis tries not to limit what you can do with your backend. As much as you can write with the regular data frame operations, Ibis is a huge matrix of tests and with different inputs to try and make sure that across backends these are as equal, behave as equally as possible. It's not just pure SQL translation. There are a lot of rewrites and things to try and maintain the correct behavior across backends as much as possible. That said, sometimes you have certain functions or things that you want to do that don't exist on a particular backend. And in that case, there are escape hatches we're not going to cover that here, but writing UDFs, including built-in UDF is basically just a way to use a function that exists on your database backend. Let's say the Levenstein distance is something that your backend supports, but isn't supported out of the box by Ibis because maybe it's not widely available. You can define a UDF there, or you can use the .SQL escape hash, which is what we're doing in these particular cases for complex regex parsing. I did mention we'll run this with Trino. So Trino does not have the same support. I think the support for regex, as far as I was able to tell, is a bit weaker. So I had to rewrite the regex vextract. So in this case, I'm going to actually go ahead and show this output for clock. This is an example. So you'll see that here when we're doing regex vextract, we're able to extract out this whole list of fields from the regex, which are all pattern matches. When I tried it on Trino, and I could be wrong because I don't have full knowledge of that backend either, I wasn't able to use those. I wasn't able to use the same syntax and had to do it in a little bit more manual and modified way. So that's an example where it's not equivalent across backends. Yeah, it's basically a design decision from Ibis in order to try to make sure you can get so you're not limited on your functionality while still being able to have, to the extent possible, if we'll see how close it is, use the same logic. this is like some of the people that kind of know using it. For example, they might be using folders locally and Spark on Databricks and in their like production environment, and so that's just like an example of what they can enable for you. Okay, so here we have our clock information. Sorry, I should have probably said, go ahead, there's another exercise directly after this. I can give maybe a minute if people haven't already moved ahead. So right now we've extracted out our hours, minutes, seconds as strings. Let's go ahead and actually try to get like the total number of seconds left per second. And so, yeah, that should be a simple kind of cast and math sort of thing. One thing that I can maybe mention while you're working on this is that so ply is like half. So ply 1 is basically as white, I'm going to play my first move. Ply 2 is actually black's first move, but it's the second ply. Ply 3 will be white's second move. Ply 4 will be black's second move. Since this is alternating, that's actually one thing we'll need to keep in mind, that 1 is like 1, 3, 5, 7 are measures of how much time white has left. 2, 4, 6, 8 are measures of how much time black has left.
So you don't have to keep it in mind for this exercise yet. We'll handle it later.
In the interest of time, I'm going to actually kind of go ahead here and load the select solution. You can see that we are just going to cast hours, minutes, and seconds to ints for hours and minutes, and you can do the whole multiplication, standard, and get seconds from hours, minutes, seconds. I don't need to explain that. Okay. What we talked about in terms of being able to like map the white and black clocks. That's how we're going to actually look at this. So we're going to first compute like what is the previous clock value, and that previous clock value will be what we can then use for the other person's clock at any given time. So this is, as a window function, it's going to take just a little bit longer to execute, but essentially we should see that like that previous clock value as another column here. So yeah. So this is the column that we created. You can see that this 60, 60, 59 is offset by 1. And so at this point, that 60 is going to actually represent what white's clock was, even though this is a black tie, even though it's black's. So based on this, kind of using that odd even logic that we talked about, we can go ahead and define our features for white clock and black clock for every single move, and we can take a look at that. One thing that you will see is that we evaluated that expression previously. We evaluated that expression again now. Since we're running in interactive mode, we're actually kind of doing some computation multiple times. But since this is for demonstration purposes, it's not going to like cache it or anything. But Ibis does provide the cache functionality if that's something you need. Yep. All right. We will still see that. So this is our white clock and black clock fields. All right. So we will see like our white clock and black clock values here. We will see that initially we don't have a black clock value just because we weren't able to look at the previous one. We can fill this in later. All right, we'll try to we can fill it in, and we can look at our clock-based features and select all of our features. Last but not least, we're going to put all of our features together. For this, we can just join the things that we created previously. So our move level features, we'll do the more specific move join first. We'll join together our eval based and our clock based features on our key of game ID and ply. And then we can join that with our game level features on the game key. And that'll give us our model input table, which is going to have our target variable, all the game level features, all our move level features, with all the appropriate names. Finally, so here we can see what that looks like for each game. So here's a game between a couple of players who are untitled, around 1,400 ELO rating. We see each of the plies. There's no, so there is a ply too. There's no guaranteed order here because we didn't order it by ply. So as a result, I don't know, it's somewhere else in the data. So that's one thing to keep in mind because as with working with a database, unless you explicitly order things, it will not necessarily order. And we can see here a white clock, black clock, including that filled. We could verify this by actually looking at the game, but for now, let's kind of move on. One of the last things we want to do before we create our model input table is we are going to create like a made eval when there's no value there. So when there's when made is on the board, there's no, it's not like, it doesn't say made in 0. We can fill in what the evaluation is based on the target here. I wouldn't worry too much about it, but essentially if white won the game and there's no made eval, we're going to fill it with a 1,000. Similarly, we're going to fill it with a negative 1,000 if black won, which is our made score. And that should be our full table. We can also take out, since we are interested in looking at the effect of time on these games, we're going to go ahead and take out our correspondence matches, as well as removing any unrated games where people may not play seriously in a way, because that could affect our model, let's say. Cool thing, Ibis allows you to kind of look at SQL for any given expression. This, of course, is backend dependent. This is what the Datta D SQL would look like. That's actually being executed under the hood. You can kind of ignore the Ibis read parquet thing. That's a temporary table created from, because we didn't actually save this to a table within Datta D. So this is from that read parquet statement. But yeah, you can see what does this ugly SQL actually look like that's being generated, rather than kind of how we build up the expression using data frames over time. Last but not least, you can go ahead and write your model input table for use. We're actually, for the next notebook, we've already also put a small version of this model input table only on the first partition of the data, so it runs a bit faster on the local machine. But yeah, I'm going to hand it over to Anjali.
Great, so we switch to the data pre-processing and modeling notebook now. This goes over the Ibis ML section. Ibis ML is a library for building machine learning pipelines. We can create recipes that will pre-process our data before training our model. And then once we have our recipe defining a series of last mile pre-processing steps, we can chain that recipe with any scikit-learn compatible estimator into a pipeline. And it seamlessly integrates with scikit-learn, XGBoost, and PyTorch through Scorch. So to get started, we're gonna pick up where we left off by reloading either that model input table, or if you want to match our results exactly, then you can load this small model input table on just like 1/6 of 1/8 data that we have. So we're gonna go ahead. Oops. That did not mean to do.
It seems like in the code space, like has files that are missing. You have more files up there than I do in my.
Do you have the small model input table there?
Is it on solutions?
Yeah, just git pull, you should be able to have that. If you still run into problems, I'm happy to take a look. I did test this on like just creating a fresh code space, so I think the sufficient files should be there.
So this shows a preview of our table. Quick show of hands, has this run for most people?
Oh, that brought along. You had to go, yeah, you had to go into the terminal and do a git pull in the terminal.
Oh, yeah.
It's in
Can you demonstrate just what we need to do?
Yeah, so what you can just do is type git stash on your terminal. So this is kind of stash away any like changes you made to make it easier to pull. Obviously better ways to do this also, but this will work. And then you can type git pull, and this should pull any latest stuff in your main. Yeah. Don't get slash pop it back, but I just did that for our demo. Yeah, so you should be able to do that, and then once you do that, under the solutions, you should have a file called, if you expand solutions, you should be able to see small model input table. Right under there. Yeah, I think you can go ahead, and then if anybody has additional questions, just feel free to let me know. So the underscore import is using Ibis's deferred expressions. I think we talked about it somewhere later on, I can't remember, but in short, so the underscore is like a special thing that allows you to refer to like the current context. If you're doing like kind of chained expressions, for example, this means that you don't need to reference like the particular table name or anything. It's going to like automatically be able to refer to the current table.
Also black magic.
Yeah, this is kind of, yeah, we'll see an example of it. But it really helps for like chaining expressions. The first notebook explicitly avoided using any of this, but as we get into like further transformations, we want to do that. Okay. All right.
Great. now we're gonna split this data set into training and test subsets randomly, with the majority of the rows in the training set. That training data will then be used to fit the recipe and the model, and the test data to evaluate model performance. One other thing is that, of course, we don't have a guaranteed order of our rows, and so therefore, in order to split, we need to decide on a key. We want to keep all of the moves from a particular game together in either test, training, or test. And so that's why we are splitting on a key of game ID and not splitting on phi as well. All right. Okay. And then down here, our X train is that data without the target, without the cheating, and our Y train, we've converted it from 0.51 to be 0, 1, 2, that's classes for a classifier, and analogously from the test data for X test and Y test. Great, so now that we have X train, we can fit and transform X train using a preprocessing recipe. So recipes are a series of last mile preprocessing steps. Those can be things like converting qualitative features to one-hot encoded dummy variables. We can transfer groups of variables like a log transform or polynomial terms, and then we could of course fill in missing values as well. They can do many of the same things as scikit-learn's dataset transformers, if you're familiar with that, but using any Ibis supported backend instead. And so for our first recipe, here's something super simple. We're going to drop any columns with 0 variance. So the column selector is ml.everything. And then we're going to drop any string columns. So fit processes our recipe using our training set. So in this case, any features with 0 variance in the training set will be slated for removal. Then transform applies the recipe to the training data, creating the final set of preprocessed features that the model will train using. Later, the recipe will also be applied to X test, but without redetermining anything in the variance. In the recipe. So for example, it doesn't matter if something has 0 variance in the test set, it matters what it did in the train set. Okay, so let's see what our fit and transformed X train looks like by running this. So we can see that is rated from above was dropped because in the previous notebook we only included rating games, which has 0 variance. And then things like the titles are also dropped because they were strings. We still have one Boolean variable left in addition to all of our numeric types, and that's its tournament. So this recipe is not yet enough to, it's not yet complete such that we can write our model. Oh, was there a question in back?
You can keep our eyes with it.
All right. So we need to encode all of our features as numeric data types. And for the inference that he'll be demonstrating later, float works best. So how would you cast all of the columns to float 64 at the end of this recipe?
So if it helps also, if you go to Ibis project.github.io/ibis-ml, you'll find the documentation for IBIS-ML, including all of these steps, such as drop 0 variance, drop, and you'll also find a cast step, which will have some examples and things of how you might be able to do this.
So I see that what we built in recipe, right? We could also easily build a cyclical pipeline, like a pipeline instead of that pipeline. Right? So where does recipe really shine as opposed to say building a pipeline?
Yeah, so recipes are going to, like kind of as Andrew mentioned, they're going to allow you to use Ibis expressions to do this in deferred way. So scikit-learn pipelines are going to essentially like convert the data to like NumPy, or I think you can now like set outputs of like pandas points. But I think that if I recall correctly, I think the computation is all happening within like NumPy data. Here, with the recipe, it's going to essentially still be, like if you're passing in the Ibis, okay. Sorry. If you're passing in an Ibis table, then, okay, fine. If you're passing in an Ibis table, then it will, and it will like continue to operate within whatever that Ibis backend is. In this case, we've already loaded it from a file, so like there hasn't been a lot of transformations there, but I can show later like how you could, so for example with Trino, we'll show like how we can have done all that feature engineering and like during inference time, and then also do the transformation using IBIS-ML without, and that's all going to be on the database, no like intermediate files, nothing going to NumPy or DigitalOcean.
Yes.
I had a question. I was seeing the recipe object and it's kind of injected into the sklearn type pipelines. How does it work with the get param, set param type of workflow that you can do parameter tuning with sklearn?
Yeah, so get params, set params are supported. There's actually a feature request, I think, from Vincent, who works at Probable, the scikit-learn company. So we did support that a few months ago, I think. In terms of hyperparameter tuning, so like technically that should allow you to do that. In terms of like kind of actually creating examples of hyperparameter tuning and things like Optuna, like that was something that was on the list of things to do, but didn't get around to yet. So happy to talk though more about that later. But yeah, the get params, set params are supported as you would with any scikit-learn estimator. Recipes are treated as an individual step, rather than like allowing scikit-learn to go into each of the steps as a full transformer, rather than allowing scikit-learn to really like go into each of the steps of the transformer, but the recipe object exposes the full set of parameters for each of the steps in the recipe.
And is this two-step pipeline tend to be how it's done? The model's the last one, and then the recipes all joined together? Everything, all that logic would be.
Yeah, generally, I mean, you could have additional scikit-learn classifiers. I think she mentioned that tried to do multiple recipes. They did not play well together, apparently. So I'm not entirely sure. That's probably something that I might need to look at. But yeah, it also makes the most sense to use Ibis ML when you have an Ibis table as input, and then because that means that you're already on whatever like backend or database, and then you stay within that context as much as possible before going to scikit-learn in these cases. This is also examples of using within scikit-learn. You can use it individually outside of scikit-learn as well. The other thing is that, so basically like, if you already go to scikit-learn context, being able to delegate then delegate to BigQuery backend doesn't really make a lot of sense because your data has already been processed and evaluated locally. So ultimately logical perspective, and apparently from how the code works perspective, I don't think you should use multiple recipes.
Cool.
Yeah, so I think it's kind of been applied at Ibis ML is less mature than Ibis. Okay. How are people doing on the exercise? Great. All right. So we simply cast everything to float 64, and then double check that I actually ran the thing. All right. So now has been, as has been asked about in unifying, we are in fact going to chain it together in a scikit-learn pipeline. It's our super simple recipe, followed by an XGBoost classifier, and this parameter or hyperparameter has been specified. And I think it should take under a minute to train here. So now that we've done this, to get a sense of our fitted XGBoost model, we'll plot feature importance, so we'll plot both average gain and average cover. So we can see that hopefully that's just pretty logical. The evaluations of the position and picking up that seem to matter, but close. But clock is also important in case one there is about to run out of time. All right. Awesome. And now we can score these on the training set. And it has been said, great, about 2/3 on each of them, so we don't seem to have overfit too much. And one thing that I'll point out right now for this is that we're treating each row, so each ply, as its own row, and that means that this is going to be hard to get very high because a lot of these predictions are on like after the first or second or whatever ply, when we have very little information about how this game is probably going to go. Great. So now we're going to predict the probabilities of each outcome for the test data set. And then we're going to define our win probability as the probability of white winning plus half of the probability of drawing. And of course, if you actually had big, large data sets, you would want to be careful about just converting to pandas. But since we're illustrating on something pretty small, it should be just fine. And then I should have done something too. Great. So one thing about this is for binary classification. So for Bernoulli variables, we of course normally use logistic loss. But we also have draws here. So we have 0.5s in our target. So logistic loss may not be totally theoretically sound, but we're going to use it here for simplicity. And what we're going to do is, so if you consider a draw, even if we correctly predict a win probability of 50%, we'd still get a log loss of about 0.3. And so we're just going to adjust that out of our metric. Plot it nicely. So we're just going to subtract off the log loss of that corresponds to perfect prediction. So if you're wondering why there are custom functions here, that's why. And great, so we perform better than if we just predicted an outcome. And obviously we do way worse than the perfect prediction. As I mentioned, hopefully our predictions get better as we get farther along in the game. So now we're going to plot, okay, this is just showing that initially we are basically predicting the mean. We're doing no better. And as things go along, we get better. But we can actually plot this. So, of course, if we throw all our features into Chantex GBoost and guess it out, we don't have a great idea of what's actually happening and whether we've totally messed up somewhere along the way. So for that, we have logistic regression. And this also illustrates a few more Ibis ML steps, because now we need to actually fill in missing values, since logistic regression doesn't handle that like Boost does, as well as normalize all of our numeric columns. As he mentioned, adding multiple recipes doesn't didn't seem to work super well. So instead, changed it together this way into a single recipe. All right, great. We're going to score this one as well. So, if you remember, these are about 0.66 for XGBoost. And okay, so for such a simple model, not too bad, but of course not as good as XGBoost. As a comparison, if you just blindly predicted white one for everything, this would be get. We do a similar prediction and loss plotting. And you see that they start off very similar and pretty similar to predicting the mean, and eventually actually do things better. Okay. Now, the reason we did want logistic regression was to be able to look at all of the coefficients. So all of these values make pretty good sense to me, except that the ELO ones actually look pretty backwards, like a higher rating decreases your chance of winning. And so to handle that, we to check whether you made a mistake, we're going to take a look at a model with only the ratings in there. See how we do. And because we didn't scale anything, so now we see that things go in the right direction that we would hope for. And we can see the probabilities of just like actually manually looking at different ratings. Turns out that a huge scale difference in this model doesn't actually correspond to a very big difference in like win probabilities, but there's a different reason for that. But it does, everything does go in the direction that we expect. Great. Awesome. So now I'll illustrate the ability to like actually create some features within Ibis ML itself for last ML feature preprocessing. And so perhaps the difference between how much time the players have left might be a useful feature. So like if white has only 5% of their time left, while black still has 95% of their time left, that might be very indicative of who's going to win, regardless of the condition on the board. So we can use this ml.mutate, which kind of corresponds to the Ibis mutate. And here we're using those underscores that we talked about before.
Since we're running low on time, maybe we can just kind of see what, like, add some of these additional features and then train the model. I think like maybe we can skip over the exercise and just kind of go to the solution for that.
Yeah. So we similarly add the difference in ratings, combine everything. It ended up like scoring very slightly better. And on this plot, you actually can't see any difference before that at all, but it turns out that that's slightly better at the beginning.
It's okay. That's just.
It's fine. It doesn't matter.
I think you can follow along and you can run through the full notebook. It should be there.
Okay. Then we can lastly see a little bit of the results. Obviously, once again, if you actually have a big name, you wouldn't want to just convert to pandas. You have a sample game where it's a grandmaster against a relatively low-rated player. And one thing we'll see is that it starts off already favoring black, the grandmaster. So as you see with the younger 0.5 to start, and ends in about 21 moves, so 40 to 5. And even a grandmaster. This is an animated tree, and it looks like for some time after this. And the next example we have, you can see later on in the game that white actually has a pretty big advantage. So 7.5 is like close to a queen up, but the model gives them a win probability of less than 0.1. And if we go down, the reason is because they are about to run out. So this shows us that in general, our model is roughly what we would have hoped.
All right. So real quickly, I know we just have a few minutes left, but wanted to show our promised part about scaling, right? So here we are going to be running the same stuff on Starburst Galaxy. So it's going to take a couple minutes to list the tables here just because the cluster needs to be warmed up. I can just really quickly show that I've got a cluster here. It's starting. It's located in Europe because our data is hosted in Europe. And this is going to be, we're going to be running, this is a 16 node Trino cluster that we're going to be running on the full month of September with. So that's going to be, well, we'll see the list of games that we're running this on, but before, like the data that we have locally, that's about 1.5 days worth. When we were doing it for the modeling, it was a smaller subset because, well, we were running on like a 4-core code space. Here we can actually see what it looks like to run at scale. When we execute this, so maybe I can actually kind of start going ahead because I have some of the results already. We can see, you can get all the games back. We did some pre-processing in order to even produce the stuff that's in the data folder locally. That will be like our removing any games that don't have evaluations. And that reduces our total count of games and moves to about that 10%. And then we will also create, we'll basically run the exact same logic. We did talk about how SQL can be a little bit different. So you'll see here that the regex and the fact that we're parsing it as 2 regex pxextract, at least with Trino, I can figure out how to get out multiple groups at once. And we have an example here of what it looks like when we're not running interactive mode. So this is like essentially the AST, the query plan that Ibis is going to be then giving to that execution engine and translating into SQL. Let me just see if that has finished warming up. Yeah, so we see our 2 tables. Now we can go ahead and execute. So as we see, some of these statements will take a little bit longer, but that's because we're running on that full set of data, especially as we're doing the count operations and things. So this will go ahead and do our feature engineering, create all of our features. This is pretty much the same code. The only parts which are changed is that SQL, sorry, the .SQL with the regex. we can see that for a model input table, what it looks like, we do our same filtering. This is essentially like a, and then this is essentially like a preview of our filtered model input table. But we can see here that we have, how many, like 5 billion-ish rows, I think, in the, or half a billion rows, I can't count right now. too many zeros. Question that was there about like Ibis, like why are we using Ibis ML over scikit-learn? We're able to, so I'm gonna just, I pick up one of those recipes, gonna load that back, and we can apply that. Here, make sure to call it like to Ibis instead of just like doctrine with a scikit-learn, because that will actually force it to NumPy and take forever. And we are able to essentially apply that recipe directly, again, executing on Trino. This is also fairly expensive little node. So like, for example, if I look at the usage, you can see that like it's been like luckily for credits, but it has spent like a few $100s already just in the cluster being out. Last thing that I want to show real quickly is scaling inference. So one of the other interesting things about Ibis ML is that we can like potentially like inference is something that we can do fully on the database or using like some database engines. We're going to go ahead and load our data here and fit a model as we did before, but we're going to go ahead and save the regressor out. One of the things which, while working on Ibis ML that learned about was this kind of cool library called LetSQL. LetSQL is something that uses Ibis under the hood, and it is able to essentially support multi-engine workflows. So here, for example, we are going to use we're going to create like a LetSQL connection, but then we have our data coming in from Datta D. We're just going to load from that model input table. And in this case, we are registering our saved XGBoost model with that, and that's going to actually transfer the data to Data Fusion and execute using an efficient Rust implementation of XGBoost to do kind of inference like more quickly. So this is just like something I want to show as like a very cool example of how you can use Ibis and Ibis ML. So here we can see like our original table as we then apply just that recipe for the pre-processing. This does require, this is why we did all the conversion to floats. And then if we're going to go ahead and do the inference, one thing that I should have done here is I should actually mutate this to be predicted equals, whoops, not prohibited inheritance, but predicted dot clip, because we are using, so this is like a very experimental library, but it only supports regressors right now, so we actually modeled this as a, or she modeled this as a regression instead. We just need to make sure our result stays between 0 and 1. Apparently the performance is very similar. That is it. I know that we've gone slightly over time, but I really appreciate it. If you are interested in this project, you can go ahead and check out ibisproject.org or the Ibis ML documentation. They're both on GitHub. Some of the other stuff we talked about, DLT Hub, you can talk to Jill that hour, look it up, as well as with LetSQL. I'm happy to share this blog article, which is kind of what I followed in order to do this. But like I said, this one is quite experimental, but I think it's just very cool what you can do. Definitely, we'll be here through the rest of the conference. Feel free to come and talk to us if you have any questions, or if you're interested in maybe even helping improve the actual live link probability model. So, yeah, thanks all.